The universe is an endless expanse of wonder, a place where the more we discover, the more we realize just how much we don't know. Look up at the night sky, and you're staring into a cosmic ocean of mysteries, some so profound that even the brightest minds on Earth still can't crack them. What lies beyond the edge of our observable universe? Why does dark energy seem to defy the very laws of physics? Are we truly alone, or is something or someone out there watching from the shadows of deep space? These aren't just questions from science fiction. They're real, unresolved enigmas that keep astronomers and physicists awake at night. And today, we're diving headfirst into 30 of the most baffling, mind-bending questions about space that science still can't answer. Think about it. Humanity has walked on the moon, sent probes to the farthest reaches of our solar system, and glimpsed galaxies billions of light years away. Yet, with every breakthrough, the cosmos throws another curveball our way. Black holes warp time and space in ways we barely understand. Unexplained radio signals from distant stars pulse through the void, hinting at phenomena we can't even name. And then there's the unsettling truth that over 95% of the universe is made of stuff, dark matter and dark energy that we can't see, touch, or fully explain. It's as if the universe is a grand puzzle and we're only holding a handful of the pieces. That's the thrill of it, though. The unknown isn't just a gap in our knowledge, it's an invitation. An invitation to explore, to question, to let our curiosity run wild. And that's exactly what we're doing here. Whether you're a space enthusiast or someone who just loves a good mystery, this journey is for you. We're about to uncover the biggest unanswered questions hanging over astronomy, physics, and the very nature of reality itself. Some might unsettle you. Others might blow your mind, but one thing's for sure, by the end you'll see the night sky and our place in the cosmos in a whole new light, so buckle up. The universe has secrets and we're digging deep to uncover them. Imagine holding a cosmic scale, one side weighed down by all the stars, planets, and galaxies we can see, the other side empty. Yet somehow the empty side is heavier. That's the bizarre reality of dark matter. It's everywhere, weaving through the universe like an invisible scaffold, holding galaxies together with its gravitational pull. We can't see it, touch it, or detect it directly, yet without it, the cosmos as we know it would fly apart. Here's how we know it exists. Stars at the edges of galaxies' orbit way too fast for the gravity of visible matter alone to keep them in place. Clusters of galaxies bend light more than they should, as if something unseen is warping space-time around them. Even the way the universe formed after the Big Bang points to an invisible hand shaping everything. The math doesn't lie. Dark matter makes up roughly 27% of the universe. But what is it? Scientists have chased shadows for decades. One leading guess: WIMP, weakly interacting massive particles. These hypothetical heavyweights barely interact with normal matter, slipping through our detectors like ghosts. Yet after years of hunting in underground labs and particle colliders, we've found nothing. Then there are actions, ultra-light particles born from quantum theory, so elusive they'd make a neutrino look obvious. But again, no cigar, the frustration is real. We've built detectors in abandoned mines, launched telescopes into orbit, even tried catching dark matter in ancient minerals deep underground. Still, it dodges us. Some theories even suggest we've got gravity all wrong, that dark matter doesn't exist, and our equations just need rewriting. But most scientists aren't ready to scrap decades of evidence. Here's the kicker. If dark matter is a particle, it's not just some cosmic placeholder, it's an entire new frontier of physics waiting to be discovered. Unlocking it could rewrite the rules of the universe. Until then, it remains the ultimate cosmic tease, all around us, shaping everything, yet forever out of reach. If dark matter is the universe's invisible glue, Dark energy is its shadowy fuel, a force so baffling it makes galaxies flee from each other at ever-increasing speeds. Picture blowing up a balloon with dots on its surface. As it inflates, the dots move apart. Now imagine the balloon suddenly starts expanding faster, as if some unseen hand is pumping air into it at an accelerating rate. That's the effect dark energy has on our cosmos. Here's what we know for sure. In the late 1990s, astronomers studying distant supernova made a jaw-dropping discovery. Instead of slowing down as expected after the Big Bang, the universe's expansion was speeding up. It was like throwing a ball in the air only to watch it rocket away faster and faster, defying gravity. The culprit, a mysterious repulsive force, dark energy, now estimated to make up a staggering 68% of the universe. But what is it? The leading theory points to Einstein's cosmological constant, a sort of built-in energy woven into the fabric of space itself. Einstein initially proposed it as a fudge factor to keep the universe static, then abandoned it as his greatest blunder when the expanding universe was discovered. Turns out he might have been right all along, just for the wrong reasons. If this constant energy exists, it would push space apart, creating the acceleration we observe. Then there's quintessence, a far stranger idea. Unlike the steady cosmological constant, quintessence imagines dark energy as a dynamic, evolving field, almost like a cosmic weather system shifting over time. Some models suggest it could grow stronger, tearing atoms apart in a big rip, or fade away, letting gravity reclaim dominance. The wildest part, we have no way to detect dark energy directly. It doesn't clump like dark matter or interact with light. Its presence is only revealed by its cosmic fingerprint, the way it stretches space-time itself. Telescopes like Euclid and the Vera Rubin Observatory are now mapping this expansion in unprecedented detail, hunting for clues in the large-scale structure of the universe. One thing's certain, dark energy isn't just a puzzle, it's a paradigm shift. If it's the cosmological constant, why is its strength so perfectly tuned to allow galaxies and life to form? If it's quintessence, what triggers its changes? The answers could rewrite not just cosmology, but our understanding of physics itself. Until then, it remains the universe's most dominant and most enigmatic force. What if our universe is just one page in an infinite cosmic library, where every possible version of reality exists simultaneously? The multiverse theory isn't science fiction. It's a serious scientific hypothesis with roots in quantum mechanics and cosmology. And it forces us to ask, are we living in the only universe, or is ours just one bubble in a frothing sea of realities? Let's start with quantum mechanics, where things get weird fast. In the 1950s, physicist Hugh Everett proposed the many worlds interpretation, suggesting that every quantum decision spawns new universes. Think of it like a cosmic choose-your-own-adventure book, except every possible outcome actually happens. When an electron goes left instead of right, or you choose coffee over tea, reality splits. Somewhere, there's a universe where dinosaurs never went extinct, where you became an astronaut, or where gravity works in reverse. It sounds outrageous, but the math holds up, and it solves one of quantum theory's biggest headaches: why we only observe single outcomes in experiments when particles exist in multiple states at once. Then there's the inflationary multiverse. According to cosmic inflation theory, our universe ballooned exponentially after the Big Bang. But what if that inflation never stopped? Some regions of space could still be stretching, creating isolated, bubble universes with their own laws of physics. Picture a boiling pot of water. Each bubble is a separate cosmos, some with stronger gravity, others with no stars at all. This idea comes straight from the equations of inflation, making it less speculative than it seems. But here's the catch: how do we test any of this? If other universes are permanently cut off from ours, does the multiverse remain forever untouchable by science? Some researchers hunt for cosmic scars, anomalies in the cosmic microwave background where our bubble might have collided with another. Others look for subtle patterns in particle behavior that hint at parallel realities tugging on our own. So far, no smoking gun. The philosophical implications are just as staggering. If infinite universes exist, does that mean everything must happen somewhere? Are there versions of you reading this script right now with only a single atom spin setting your lives apart? The multiverse blurs the line between science and metaphysics, forcing us to ask, is this elegant physics or just an untestable escape hatch for explaining our universe's improbable fine-tuning? One thing's certain: the multiverse pushes the boundaries of imagination. Whether it's real or not, the idea alone reshapes how we see reality. Maybe we're alone in the cosmos. Or maybe, just beyond the edge of perception, countless other universes hum with their own untold stories. Black holes are cosmic contradictions, regions where the laws of physics as we know them break down completely. Picture this: a star collapses under its own gravity, crushing matter into an infinitely dense point called a singularity. Around it lies the event horizon, a boundary so sinister that once anything crosses it, even light can't escape. But here's where things get weird. According to Einstein's general relativity, time slows to a stop at the event horizon, and the singularity warps space-time beyond recognition. Yet quantum mechanics tells a different story, insisting information can't just disappear. This clash creates one of the biggest paradoxes in modern physics. Take Hawking radiation, for example. In the 1970s, Stephen Hawking proposed that black holes aren't completely black. Thanks to quantum fluctuations near the event horizon, particles and antiparticles pop into existence. Occasionally, one falls in while the other escapes, making the black hole slowly evaporate over eons. But here's the problem: if the black hole vanishes, what happens to all the information it swallowed? Quantum mechanics says information must be preserved, but relativity suggests it's lost forever. This information paradox has divided physicists for decades. Some argue the information is scrambled and leaked back out via Hawking radiation. Others think it's trapped in a hidden layer of reality inside the black hole. Then there's the firewall paradox. Imagine crossing the event horizon. According to relativity, you'd feel nothing at first, a principle called no drama. But quantum physics suggests you'd immediately hit a searing wall of high-energy particles. Both can't be true. This isn't just theoretical wrestling. It hints at a fundamental flaw in our understanding of gravity and quantum fields. The wildest idea, holographic duality, which suggests everything inside a black hole is encoded on its surface like a cosmic DVD. If true, it could mean our entire universe is a projection of information stored at its boundaries. Black holes aren't just cosmic vacuum cleaners, they're laboratories for the most extreme physics imaginable, forcing us to rethink reality itself. Until we crack their secrets, they remain the ultimate enigmas of the cosmos. The night sky is filled with countless stars, each one a potential sun to another world, so where is everybody? That's the haunting question at the heart of the Fermi paradox, named after physicist Enrico Fermi, who famously asked it over lunch in 1950. The math seems undeniable. With hundreds of billions of stars in our galaxy alone, many hosting Earth-like planets, the universe should be teeming with civilizations. Yet after decades of listening, searching, even broadcasting our own presence, we've found nothing but silence. Consider the numbers. The Drake equation, formulated by astronomer Frank Drake, estimates the potential number of intelligent civilizations by factoring in variables like star formation rates, habitable planets, and the odds of life emerging. Even using conservative estimates, the equation suggests there should be thousands, if not millions, of advanced societies out there. So why haven't we seen a single signal, artifact, or cosmic hello? One possibility is that we're looking in the wrong way. SETI, the search for extraterrestrial intelligence, has scanned the skies for radio waves and laser pulses for decades. But what if advanced civilizations communicate using neutrinos, quantum entanglement, or something we haven't even imagined? Or maybe they've moved beyond physical probes, leaving behind Dyson spheres or other megastructures we're only beginning to recognize as artificial. Then there's the chilling Great Filter hypothesis. It suggests that somewhere between the rise of life and interstellar expansion, there's a wall, a catastrophe or evolutionary hurdle so deadly that almost no civilization survives it. Are we on the brink of encountering it, or did we somehow slip past it undetected? But let's not overlook the simplest answer: distance. Space is unimaginably vast. Even if civilizations thrive, the gaps between them might be so enormous that signals take millennia to cross the void. By the time a message arrives, the sender could be long extinct. The search isn't hopeless, though. Telescopes like JWST are analyzing exoplanet atmospheres for biosignatures, gases like oxygen or methane that hint at life. Missions to Europa and Enceladus hunt for microbes in icy oceans. And projects like Breakthrough Listen are scanning millions of stars with unprecedented precision. Perhaps we're alone, or maybe we're on the cusp of the greatest discovery in history. Either way, the silence isn't empty, it's a question, and the answer could change everything. How did life emerge from lifelessness? It's one of the most profound questions science faces, a puzzle buried under billions of years of time. Somewhere in Earth's chaotic early history, simple molecules crossed an invisible threshold, becoming something capable of growth, reproduction, and evolution. But how? Two leading theories dominate the debate. Abiogenesis, the idea that life arose from Earth's primordial chemistry, and panspermia, the possibility that life's building blocks hitched a ride here on comets or asteroids. Let's rewind to Earth 4 billion years ago. The planet was a hellscape: volcanoes spewing noxious gases, lightning lashing sulfuric skies, oceans churning under relentless asteroid bombardment. Yet in this chaos, the ingredients for life were stirring. The Miller-Urey experiment in the 1950s showed that simple molecules like water, methane, and ammonia, common in Earth's early atmosphere, could form amino acids when zapped with electricity. These are the very blocks that build proteins, hinting that life's recipe might have been written in the planet's violent chemistry. Then there's the RNA world hypothesis. DNA is life's blueprint today, but it's too complex to have been the first molecule. RNA, however, can both store genetic information and catalyze reactions, a multitasker possibly capable of kickstarting life. Imagine shallow volcanic pools where RNA strands formed, replicated, and even competed, setting the stage for Darwinian evolution before cells existed. Recent experiments show RNA can self-assemble under plausible early Earth conditions, giving this theory serious weight. But what if life didn't start here at all? Enter panspermia. The discovery of amino acids on meteorites like Murchison proves space is littered with organic molecules. Some extremophiles, microbes thriving in Earth's harshest environments, can survive the vacuum of space, fueling speculation that microbes might have traveled between planets inside rocks. The comet impact that killed the dinosaurs also splashed earthly microbes into space. Could the reverse have happened? The wild card: deep-sea hydrothermal vents. These mineral-rich chimneys host entire ecosystems thriving without sunlight, powered by chemosynthesis. Their labyrinthine structures might have concentrated chemicals, creating natural laboratories for life's first reactions. Meanwhile, extremophiles found in boiling acid or Antarctic ice push the limits of where life can exist, raising the spine-tingling possibility that if life started here under such extremes, it could have done so elsewhere in the cosmos too. The truth is, we don't know yet, but every discovery, from synthetic cells to interstellar organic molecules, brings us closer to answering whether life's origin was a cosmic fluke or an inevitable twist in the universe's story. And if we crack it, we might finally understand just how alone or how accompanied we truly are. Will the universe end with a bang, a whimper, or a tear? The answer lies in a cosmic tug-of-war between gravity and dark energy, and right now, dark energy is winning. Scientists have theorized several possible fates for our universe, each more dramatic than the last. Whether it collapses in on itself, fades into icy darkness, or gets ripped apart atom by atom depends on forces we're still struggling to understand. First, consider the Big Crunch, a cosmic reversal of the Big Bang. If dark energy weakens over time, gravity could finally gain the upper hand. Galaxies would stop racing apart and begin falling back together. Space itself would contract, temperatures soaring as everything is crushed into an unimaginably dense singularity. It's a poetic symmetry, the universe ending where it began. But current evidence suggests this scenario is unlikely. Dark energy shows no signs of fading, and the expansion rate keeps accelerating. Then there's heat death, the bleakest of endings. Imagine trillions of years from now, stars burning out one by one until the universe goes dark. Black holes evaporate via Hawking radiation, leaving behind only a thin soup of photons and subatomic particles, stretched so far apart that no new interactions occur. Time itself might lose meaning in this frozen, entropy-maximized void. This scenario aligns with our current observations. Dark energy keeps pushing galaxies apart until the cosmos becomes a vast, lifeless desert. But the most violent possibility, the Big Rip, if dark energy grows stronger over time, its repulsive force could eventually overpower gravity, then electromagnetism, then even the nuclear bonds holding atoms together. First, galaxies would be shredded, then stars and planets. Finally, in the last terrifying moments, every molecule, every proton, every quark would be torn apart. The universe wouldn't just fade, it would explode into non-existence. The deciding factor, the universe's curvature. If space is flat, as current data suggests, expansion will continue indefinitely. But if it's positively curved like a giant four-dimensional sphere, a big crunch remains possible. And if dark energy behaves like quintessence fluctuating unpredictably, all bets are off. One thing's clear, the universe's fate isn't written yet. Every new measurement of supernova, every map of the cosmic microwave background, brings us closer to knowing whether we're headed for fire, ice, or oblivion. And that knowledge might just reveal the deepest secrets of dark energy and reality itself. At the birth of the universe, the Big Bang should have created equal amounts of matter and antimatter, particles and their mirror image opposites. When matter and antimatter meet, they annihilate in bursts of pure energy. So why didn't the cosmos cancel itself out immediately? Why are we here at all? This is the mystery of matter-antimatter asymmetry, and solving it could reveal one of reality's deepest secrets. For every particle, there's an antiparticle with opposite charge. Electrons have positrons, protons have antiprotons, and so on. According to physics' most fundamental symmetries, the early universe should have produced these pairs in perfect balance. But something tipped the scales. Today, we live in a universe dominated by matter, stars, planets, and galaxies made of normal particles with barely a trace of antimatter left. That imbalance is tiny, just one extra matter particle for every billion annihilations, but without it, existence as we know it wouldn't be possible. The first clue came in 1964 with the discovery of CP violation. CP stands for charge parity, a symmetry that should make particles and antiparticles behave identically when their charges and spatial orientations are flipped. But researchers found that kaon's rare subatomic particles decayed slightly differently from their antimatter counterparts. This was like finding a coin that lands on heads more often than tails, violating the expected symmetry. While the effect was minuscule, it proved the laws of physics could favor matter over antimatter. But CP violation alone isn't enough to explain our matter-dominated universe. Enter baryogenesis, the process that might have tipped the cosmic scales. Theories suggest extreme conditions right after the Big Bang, like temperatures 1 billion times hotter than the Sun, could have triggered reactions that produced more matter than antimatter. Some scenarios involve hypothetical heavy particles decaying unevenly, while others invoke quantum fields that briefly skewed the balance during cosmic inflation. CERN LHCb experiment is hunting for answers by smashing particles together and studying their decays with unparalleled precision. Recently, they observed CP violation in beauty quarks, adding another piece to the puzzle. Meanwhile, deep underground, detectors like Super Kamiok and watch for neutrinos particles that might hold the key, as they oscillate between matter and antimatter states in ways we're only beginning to understand. The stakes couldn't be higher. If we uncover why matter won out, it could rewrite textbooks from particle physics to cosmology. Some theories even link it to dark matter or hidden dimensions. Whatever the answer, it's hiding in the faintest imbalances of nature, waiting to reveal why the universe didn't vanish before it even began. We can see galaxies billions of light years away, but what lies beyond that cosmic horizon, the edge of our observable universe? The unsettling truth is, we'll never know for sure. Light from those distant regions hasn't had time to reach us since the Big Bang 13.8 billion years ago. But here's the mind-bending part. The observable universe might just be a speck inside something far grander. Perhaps an infinite expanse stretching forever into the dark. Picture a ship sailing toward the horizon on an endless ocean. No matter how far it travels, new horizons always appear. The observable universe works the same way. Every day, light from previously unseen regions finally reaches us, expanding our cosmic view. But inflation theory suggests the entire universe could be at least 150 sextillion times larger than what we see, a number so vast it defies comprehension. If you traveled at light speed forever, you'd never reach the edge because space itself is stretching faster than anything can move through it. This leads to wild possibilities. One is the eternal inflation model, where our universe is just one bubble in a frothing multiverse. Beyond our cosmic horizon, other bubble universes might exist, each with different physical laws, some with stronger gravity, others where atoms never formed. Some could even harbor alien civilizations gazing out at their own observable limits, equally oblivious to us. Then there's the shape of space itself. Einstein showed that the universe could be finite yet unbounded, like the surface of a balloon. If you flew straight long enough, you might loop back to where you started. But measurements of cosmic microwave background radiation suggest space is flat, meaning it could truly stretch to infinity. An endless cosmos raises haunting questions. Are there copies of Earth out there with identical versions of you reading this script? In an infinite universe, every possible configuration of matter would repeat somewhere. The most unnerving idea: we're fundamentally trapped. No signal, no probe, no telescope can ever peer beyond our observable horizon. The rest of the universe is forever hidden by the sheer speed of light and the relentless expansion of space. It's the ultimate cosmic tease, knowing there's more, but being forever locked out. Yet that mystery drives science forward. By studying the patterns of galaxies, the slight warping of space-time, and the echoes of the Big Bang, we piece together clues about the unseeable whole. The universe may never reveal its full secrets, but the pursuit of those answers reminds us how small and how extraordinary our corner of existence truly is. The Big Bang wasn't just an explosion, it was the birth of time, space, and everything we know. But what sparked it? What existed before the beginning? Trying to answer that feels like asking what's north of the North Pole. Our physics hits a wall at the moment of singularity, where all equations break down. Yet scientists have daring theories that stretch the boundaries of imagination, each offering a different glimpse into the unknowable. One radical idea is the cyclic universe, a cosmos without true beginning or end. Imagine the universe as a cosmic accordion, expanding and contracting in an endless cycle. Each Big Bang is just the start of a new phase, preceded by a big crunch, where everything collapses back into a singularity before rebounding. This model, rooted in string theory and brain cosmology, suggests our universe exists on a membrane colliding with another in higher dimensional space. When these brains smash together, the energy ignites a new Big Bang. The appeal, it dodges the need for a definitive starting point, replacing it with an eternal rhythm of creation and destruction. Then there's quantum fluctuation, the notion that our universe popped into existence from nothing, or rather, from the roiling foam of quantum uncertainty. On the tiniest scales, particles blink in and out of existence all the time, borrowing energy from the vacuum before vanishing again. Some theories suggest a similar fluctuation in the primordial quantum field could have birthed an entire universe. In this view, the Big Bang wasn't a singular event but a random, albeit staggeringly improbable bubble in an infinite quantum sea. But how can nothing create something? That's the nothingness paradox. Even empty space isn't truly empty. It's fizzing with potential energy. Theoretical physicist Lawrence Krauss argues that the total energy of the universe might actually sum to zero, gravity's negative energy perfectly cancelling out matter's positive energy. If true, the universe could have arisen from zero net input like a perfect cosmic free lunch. The problem, these ideas live where science blurs into philosophy. Without a theory of quantum gravity, we can't peer past the Planck epoch, the first fraction of a second after the Big Bang where known physics fails. Experiments like those at the Large Hadron Collider recreate extreme conditions, but we're still missing the equations that unite quantum mechanics with general relativity. Perhaps the most humbling thought is this: the question itself might be flawed. Time, as we understand it, may have begun with the Big Bang, making before meaningless. The universe might not need a cause, it could simply be a brute fact of existence. Whether cyclical, quantum-born, or something beyond our comprehension, the origin of everything remains the ultimate mystery, reminding us that some answers lie forever beyond the horizon of human knowledge. Wormholes, cosmic shortcuts stitching distant corners of spacetime together, aren't just science fiction. They emerge straight from Einstein's equations of general relativity, where gravity warps the fabric of reality itself. In 1935, physicists Albert Einstein and Nathan Rosen theorized that black holes might connect to white holes, regions where matter and energy gush outward through bridges in spacetime. These Einstein-Rosen bridges became the first mathematical glimpse of wormholes, but could they really exist? The math is tantalizing. Picture spacetime as a folded sheet of paper. A wormhole would be like poking a pencil through the fold, creating a tunnel between two distant points. Traveling through it could let you cross thousands of light years in moments, sidestepping the universe's speed limit. But here's the catch: holding a wormhole open requires something called exotic matter, a substance with negative energy density. Unlike normal matter, which gravitationally attracts, exotic matter would repel, propping the wormhole's throat open against the crushing force of gravity. The problem: exotic matter isn't just rare, it might be impossible. Quantum field theory allows for fleeting instances of negative energy, like the Casimir effect, where closely spaced metal plates create a tiny repulsive force in a vacuum. But scaling that up to stabilize a wormhole, you'd need astronomical amounts of this phantom material, and no one knows where to find it, or if it can even exist in usable quantities. Then there's the instability issue. Even if a wormhole formed naturally, calculations suggest it would snap shut instantly unless exotic matter bolted it open. Some theories propose cosmic strings, hypothetical, ultra-dense defects in spacetime, could stabilize wormholes, but these are even more speculative. And let's not forget radiation. Any attempt to pass through might trigger a lethal feedback loop of energy, vaporizing anything daring enough to enter. Sci-fi loves wormholes, from Interstellar's visually stunning Gargantua to Stargate's ancient portals, but reality is far messier. Modern physicists like Kip Thorne have refined the math, showing traversable wormholes could exist if exotic matter does. Others suggest wormholes might only be microscopic, forged in the quantum foam of the early universe. The wildest idea, wormholes could be time machines. According to general relativity, manipulating one end of a wormhole, say, by moving it near a black hole, could create a path where you exit before you entered. But this invites paradoxes like going back to prevent your own birth, making many physicists skeptical. For now, wormholes remain hypothetical, straddling the line between profound theory and cosmic pipe dream. But their possibility keeps scientists probing, because if they're out there, they'd rewrite not just physics textbooks, but the very rules of exploration itself. The moon shouldn't exist, at least not the way it does on paper. It's a cosmic oddity, defying expectations at every turn. Its composition is eerily similar to Earth's mantle, yet it lacks the volatile elements and iron core we'd expect from a celestial body born alongside our planet. This bizarre mismatch has fueled one of the most dramatic origin stories in science, the giant impact hypothesis, but even that leaves glaring questions unanswered. Let's start with the moon's uncanny resemblance to Earth. Lunar rocks brought back by Apollo astronauts revealed oxygen isotope ratios nearly identical to Earth's, a fingerprint so specific it suggests the two bodies share a genetic link. But here's the twist: the moon is bone dry. It's missing lightweight elements like potassium and sodium that should have been abundant if it formed from the same primordial soup as Earth. Even more puzzling, its core is tiny, just 1 to 2% of its mass compared to Earth's 30%. If the moon was a sister world, why is it so stripped down? This is where the giant impact hypothesis comes in. Picture a Mars-sized object nicknamed Theia smashing into a young, molten Earth over 4 billion years ago. The collision would have vaporized Theia and chunks of Earth's mantle, hurling debris into orbit where it coalesced into the moon. The model explains the isotope match and the lack of a hefty iron core. Theia's metal-heavy heart would have sunk into Earth, leaving the moon with scraps. But simulations reveal a flaw. If Theia hit head-on, the moon should carry more of its alien isotopes. If it was a glancing blow, why does the moon look so Earth-like? Then there's the moon's curious magnetism. Ancient lunar rocks bear traces of a magnetic field. Something so small shouldn't have had one strong enough to leave a record. Did its core once churn violently before freezing solid? Or was Earth's magnetosphere temporarily lending its power during their close cosmic dance? The plot thickens with the moon's mass guns, hidden pockets of dense material lurking beneath its seas. These mass concentrations warp lunar gravity, tugging on orbiting spacecraft in ways that still baffle scientists. Some suggest they're the fossilized remains of asteroid impacts, while others theorize they're relics of the moon's fiery birth, dense magma blobs that never fully mixed. Every unanswered question forces us to rethink the moon's violent past. Was Theia's impact more complex than we imagined? Could multiple collisions have sculpted the moon we see today? Or is there a stranger truth buried in those cratered highlands, waiting for the next rover or astronaut to uncover? One thing's clear: our nearest celestial neighbor is anything but ordinary. In the vast quiet of space, there are flashes so intense they outshine entire galaxies, and they last less time than it takes to blink. Fast radio bursts, or FRB, are among the universe's most enigmatic signals, pulses of radio waves packing the energy of 500 suns into just milliseconds. First discovered in 2007, these cosmic fireworks arrive without warning, sometimes repeating in patterns that defy explanation. Are they the death cries of collapsing stars, messages from advanced civilizations, or something even stranger? The leading suspect, magnetars neutron stars with magnetic fields so powerful they could strip the electrons from your atoms from 1,000 kilometers away. When these hypermagnetic monsters undergo starquakes or magnetic reconnection, they might unleash bursts of energy that ripple across the cosmos. One smoking gun came in 2020 when astronomers traced an FRB to a magnetar in our own galaxy. The burst looked identical to those from distant galaxies, suggesting at least some FRBs originate from these extreme objects. But here's the catch: not all FRBs fit the magnetar mold. Some repeat randomly, others in precise cycles, like one that flares every 16 days like clockwork. Then there's the alien question. FRBs are narrow-band signals, meaning they're concentrated at specific frequencies similar to how human-made communications work. Could they be propulsion beams from alien spacecraft, as Harvard's Avi Loeb has speculated? The idea isn't as far-fetched as it sounds. A solar-powered light sail would need a planet-sized radio transmitter to push it to relativistic speeds, potentially creating the very signatures we detect. But most scientists remain skeptical. The sheer energy required makes intentional signaling unlikely, and natural explanations aren't exhausted yet. Perhaps the weirdest twist is that some FRBs come with a side of polarization. Their radio waves twisted as if passing through a cosmic magnetic labyrinth. This suggests they've traveled through incredibly dense environments, like the outskirts of black holes or the remnants of supernova explosions. One repeating burst even changed its polarization angle over time, hinting at a turbulent, evolving origin. The mystery deepens with FRB 2012-11-2, a repeater living inside a dwarf galaxy enshrouded in chaotic magnetic fields. Is it a young magnetar wrapped in debris from its explosive birth? Or something entirely new? With each discovery, FRBs raise more questions than answers. What's certain is this: these fleeting cosmic whispers are rewriting our understanding of the universe's most extreme physics, 1 millisecond at a time. Time travel isn't just the stuff of sci-fi, it's woven into the fabric of physics itself. Einstein's theory of relativity tells us that time isn't a rigid, universal clock ticking the same for everyone. Instead, it's fluid, stretching and compressing based on speed and gravity. Imagine an astronaut blasting off at near light speed. While years pass for them, decades might fly by on Earth, a phenomenon called time dilation. It's been tested. Atomic clocks on fast-moving jets tick ever so slightly slower than those on the ground. So, in a very real sense, traveling to the future is already possible. But what about going back? That's where things get wild. General relativity allows for solutions known as closed time-like curves, paths through warped spacetime that loop back on themselves, creating a bridge to the past. Picture a cosmic whirlpool where space and time twist so tightly that the end of your journey connects to the beginning. Theoretically, if you could traverse such a curve without getting shredded by tidal forces, you might return to your own past. Some models suggest these curves could form around rotating black holes or cosmic strings, hypothetical, ultra-dense flaws in spacetime. But time travel comes with a nasty catch: paradoxes. The grandfather paradox is the classic example. What if you went back and prevented your own birth? If you never existed, how could you have traveled back to change anything? It's a logical knife edge that's puzzled physicists for decades. Some argue the universe might self-correct, bending events to preserve consistency. Maybe you'd fail to stop your grandfather's meeting with your grandmother, or some quantum fluke would intervene. Others propose parallel timelines where your actions spawn a new, alternate reality, leaving the original history untouched. Stephen Hawking had a different take. He believed nature might outright forbid time travel through what he called the chronology protection conjecture. Just as we can't divide by zero in math, perhaps the laws of physics erect an impenetrable barrier to stop closed time-like curves from forming. The idea gained traction when researchers found that quantum effects like vacuum fluctuations might spiral out of control near a time machine's threshold, creating infinite energy that destroys the wormhole before it can be used. The wildest twist: some experiments hint that quantum particles might already be cheating. In certain setups, photons appear to influence events in their own past, a phenomenon called retrocausality. It's not quite Doc Brown's DeLorean, but it suggests time's arrow might be more flexible at microscopic scales. For now, time travel remains a tantalizing maybe. The math allows it, but the universe seems to guard its secrets fiercely. Whether it's paradoxes, quantum firewalls, or some deeper law we haven't uncovered, one thing's clear. If time travel is possible, it won't be as simple as flipping a switch. It'll demand rewriting our understanding of reality itself. In the vast emptiness of space where the laws of physics should reign supreme, two tiny spacecraft defied expectations and left scientists scratching their heads for decades. The Pioneer anomaly refers to the baffling deceleration of NASA's Pioneer 10 and 11 probes as they journeyed beyond the solar system. These rugged explorers, launched in the early 1970s, were expected to coast through the void with near-perfect predictability. Yet by the 1980s, tracking data revealed something impossible. Both probes were slowing down slightly more than calculations allowed. The discrepancy was tiny, about 300 million times weaker than Earth's gravity. But in the precision-driven world of orbital mechanics, even a whisper of unexpected force demands an explanation. At first, engineers suspected mundane causes. Maybe it was thermal radiation heat from the probe's nuclear power sources leaking unevenly and giving them a gentle push backward. Pioneer's design made this plausible. Its antenna acted like a flashlight beam, emitting infrared radiation primarily in one direction. But when researchers painstakingly reconstructed the spacecraft's heat signatures, the numbers didn't quite add up. Thermal effects could account for only about a third of the observed deceleration. That left a glaring gap, one that invited wilder theories. Could this be a hint of new physics? Some theorists proposed modifications to Einstein's general relativity, suggesting gravity might behave differently at extremely weak accelerations or vast distances. Others floated the idea of unseen dark matter dust dragging on the probes, or even the gravitational pull of hypothetical objects lurking beyond Pluto. The most radical idea, a flaw in our understanding of inertia itself, a crack in Newton's first law. Then, in 2012, a team of researchers analyzing decades of telemetry data announced a breakthrough. By reconstructing Pioneer's heat distribution with unprecedented detail, accounting for every watt of power dissipated by its instruments and radioactive decay, they concluded thermal radiation could explain most, if not all, of the anomaly. Case closed, not quite. Skeptics noted lingering uncertainties in the models, and some anomalies in the data stubbornly refused to align. The Pioneer anomaly stands as a cautionary tale. Even in an age of gravitational wave detectors and quantum computers, the universe still holds subtle surprises. Whether it was mundane engineering or something more profound, the mystery reminds us that exploration doesn't end when the rockets stop firing. Sometimes, the most thrilling discoveries emerge from the quietest whispers in the data. Deep in the cosmos, hidden behind the thick veil of our own Milky Way stars and dust, something massive is pulling entire galaxies, including ours, toward it at over 600 kilometers per second. Astronomers call this mysterious force the Great Attractor, and its sheer gravitational might is rewriting our understanding of the universe's largest structures. Yet, despite decades of research, we still don't know exactly what it is, because part of it lies in the zone of avoidance, a region of the sky obscured by our galaxy's glare. The Great Attractor first made itself known in the 1970s when scientists noticed galaxies in our local supercluster, including the Milky Way, were all streaming toward the same patch of space in the constellation Centaurus. The motion defied expectations. The universe's expansion should be carrying galaxies apart, but here they were, drawn like moths to a cosmic flame. Initial calculations suggested this hidden heavyweight had the mass of tens of thousands of Milky Ways, enough to bend the paths of galaxies hundreds of millions of light-years away. But studying it is like trying to hear a whisper in a hurricane. The densest part of the Milky Way's disk blocks our view, absorbing visible light and radio waves. It's called the zone of avoidance because astronomers traditionally avoided observing there until the Great Attractor forced them to rethink. Modern X-ray telescopes like Chandra and infrared observatories like WISE have begun piercing the veil, revealing galaxy clusters and filaments hinting at something even bigger. One leading theory suggests the Great Attractor is the core of the Laniakea supercluster, a colossal web of galaxies spanning 500 million light-years with the Norma cluster at its heart. Laniakea, Hawaiian for immeasurable heaven, lives up to its name. It's an oceanic current of galaxies flowing toward this gravitational anchor. But some researchers argue even Laniakea might be part of something larger, like the Vela supercluster, a newly detected structure adding to the mystery. Then there's the dark flow hypothesis. Observations show clusters beyond Laniakea also moving toward the same point, hinting at an even grander attractor. Perhaps a concentration of dark matter so dense it warps the fabric of the cosmos on scales we've barely mapped. Others speculate it could be a cosmic string, a hypothetical defect in spacetime left over from the Big Bang, or even the gravitational shadow of a parallel universe tugging on our own. What makes the Great Attractor so thrilling is its defiance of cosmic isolation. Most structures in the universe are receding from us due to dark energy's expansion. Yet here, gravity is staging a rebellion, proof that even on the grandest scales, the universe is still full of surprises. As new telescopes peer deeper into the zone of avoidance, one thing's certain: whatever's lurking there will rewrite the story of our corner of the cosmos. Some particles hurtling through space carry more energy than a major league fastball packed into a single subatomic speck. These are ultra-high-energy cosmic rays, and their existence pushes the boundaries of physics. Where do they come from? How do they reach such impossible speeds? And why haven't they disintegrated before reaching us? The answers might lie in the most violent corners of the universe, or defy our understanding of reality itself. Cosmic rays are mostly protons or atomic nuclei, but the highest energy ones are in a league of their own. The "oh my god" particle, detected in 1991, had the kinetic energy of a brick dropped from waist height, all concentrated into a single proton moving at nearly light speed. For scale, that's 40 million times more energetic than particles in the Large Hadron Collider. Such extreme energy shouldn't exist. According to the Greisen-Zatseping-Kuzmin-Gizike cutoff, cosmic rays above a certain threshold should lose energy as they collide with photons from the cosmic microwave background, the faint afterglow of the Big Bang. Yet here they are, defying expectations. So what's launching them? Active galactic nuclei, supermassive black holes devouring matter are prime suspects. As gas spirals into these monsters, magnetic fields could whip particles to near light speed like a cosmic slingshot. Another contender, gamma-ray bursts, the universe's most powerful explosions. When a massive star collapses or neutron stars merge, the resulting fireball might accelerate particles to unheard-of energies. The problem: these sources are often billions of light-years away. By the time cosmic rays reach us, the Gizike effect should have sapped their strength. Unless they're not traveling as far as we think, that's where the paradox deepens. If these rays came from nearby, we'd expect to pinpoint their origin. Yet the sky shows no obvious hotspots. One theory suggests they're deflected by intergalactic magnetic fields, making their paths too tangled to trace. Others propose they're the decay products of hypothetical super-heavy dark matter particles winking out of existence in our galactic backyard, releasing bursts of energy that mimic distant sources. Then there's the curveball. These rays might be revealing flaws in our physics. Could Lorentz invariance, the bedrock of Einstein's relativity, break down at such extreme energies, letting particles cheat the Gizike limit? Experiments like the Pierre Auger Observatory are hunting for clues, mapping cosmic rays with unprecedented precision. Every detection is a puzzle piece, hinting at forces beyond our current grasp. Whether they're messengers from black holes, relics of dark matter, or signs of new physics, ultra-high-energy cosmic rays are more than curiosities. They're probes into the universe's most extreme environments. And with each one that strikes Earth's atmosphere, we get a fleeting glimpse into the cosmic accelerators we're only beginning to imagine. We think we know the universe's age, 13.8 billion years, but that number is at the center of a cosmic tug-of-war shaking the foundations of modern cosmology. On one side, we have the Planck satellite's meticulous mapping of the cosmic microwave background, the afterglow of the Big Bang. On the other, cutting-edge measurements of nearby galaxies using pulsating stars and exploding supernova. Both methods are precise, both are backed by Nobel Prize-winning science, and yet they disagree by hundreds of millions of years. This isn't just a rounding error. It's a full-blown crisis dubbed the Hubble tension, and solving it might require rewriting the rules of the cosmos. Let's start with Planck's approach. By analyzing subtle temperature fluctuations in the cosmic microwave background, scientists can calculate how fast the universe was expanding shortly after the Big Bang. Plug those early conditions into our standard model of cosmology, and you arrive at an expansion rate called the Hubble constant of about 67 kilometers per second per megaparsec. That translates neatly to a 13.8 billion-year-old universe, but when astronomers measure the Hubble constant directly using local methods, like tracking the distances and velocities of Cepheid variable stars and Type Ia supernova, they get a significantly faster expansion, roughly 73. At first glance, the difference seems small, but over cosmic distances it adds up. If the universe is expanding faster today than our models predict, it might actually be younger than we thought by a non-trivial margin. So who's wrong? The cosmic microwave background is arguably our most pristine snapshot of the infant universe, unaffected by later cosmic drama. But local measurements have their own strengths. They're grounded in well-tested physics, like the predictable brightness of supernova. Neither camp has found a glaring flaw in their methods, which suggests the discrepancy might be real, a clue that our understanding of the universe is incomplete. One tantalizing possibility is dark energy. The mysterious force accelerating cosmic expansion isn't constant after all. Maybe it's growing stronger, throwing off our calculations. Alternatively, there could be unknown particles like a new type of neutrino, subtly altering the early universe's evolution. Some theorists even speculate our universe briefly inflated faster than we thought, leaving imprints that skew today's measurements. The stakes couldn't be higher. If the Hubble tension holds, it could mean our cosmic timeline is off, or worse, that we're missing a fundamental ingredient in the recipe of reality. New telescopes like the James Webb Space Telescope are now joining the hunt, cross-checking distances to ancient galaxies with unprecedented precision. Whatever they find, one thing's clear: the universe's age isn't just a number, it's a mystery we're still unraveling. Out of all the stars in our galaxy, none have baffled astronomers quite like KIC 8462852, better known as Tabby's star. Named after astronomer Tabitha Boyajian, who first documented its bizarre behavior, this otherwise ordinary star flickers and dims in ways that defy every known natural explanation. Imagine a candle flame that doesn't just flicker occasionally but plunges into near darkness at random intervals, sometimes dropping in brightness by a staggering 22% before bouncing back. Stars don't do that, at least not without a reason, and Tabby's star has refused to give up its secrets. The mystery began in 2015 when data from NASA Kepler Space Telescope revealed the star's erratic light patterns. Unlike the predictable dimming caused by orbiting planets, Tabby's star showed irregular, jagged dips, some lasting days, others weeks with no clear rhythm. The most dramatic event saw its light output plummet by nearly a quarter. Natural explanations crumbled under scrutiny. A young star might have a clumpy disk of debris, but Tabby's star isn't young. A swarm of comets could block its light, but you'd need thousands of giant comets passing in front of it simultaneously, a statistical impossibility. Even a catastrophic planetary collision wouldn't produce these patterns. That's when speculation veered into science fiction. Could this be evidence of alien megastructures, a Dyson swarm of solar collectors built by an advanced civilization to harness the star's energy? The idea, first proposed by astronomer Jason Wright, wasn't entirely far-fetched. After all, if a civilization reached Type 2 on the Kardashev scale, capturing a star's power would be logical. The irregular dips might align with construction phases or shifting megastructures. For a brief, thrilling moment, humanity wondered if we were staring at the signature of cosmic neighbors. But science favors the mundane over the miraculous. Follow-up studies found the star's dimming was wavelength-dependent, meaning some colors of light were blocked more than others. That pointed to dust, not solid megastructures. Further observations revealed the dust was asymmetrical, possibly in a trailing cloud or eccentric orbit, explaining the erratic dimming. Yet even this solution raised new questions. Why is the dust arranged so chaotically? What's replenishing it to keep the dimming events ongoing? And why does the star's long-term brightness show a gradual, century-long decline? The latest research suggests a tortured planetary system, perhaps a shattered world or a captured interstellar object spreading debris in odd configurations. Others propose a stellar companion stirring up chaos. What's certain is this: Tabby's star has rewritten the playbook on stellar behavior. Every new observation peels back another layer, revealing just how little we truly understand about the cosmos. Whether it's dust, aliens, or something even stranger, this enigmatic star reminds us that the universe thrives on mysteries, and the best ones refuse to be solved easily. The universe might be far stranger than it appears, not just vast in space and time, but in dimensions we can't see or touch. We're used to living in a world of three spatial dimensions: up and down, left and right, forward and backward, plus time as the fourth. But what if there are more? According to string theory, the leading candidate for a unified theory of physics, the fabric of reality could be woven from tiny, vibrating strings in a cosmos with at least 10 dimensions. The catch: all but 4 of them are curled up so tightly that we'll never notice them in everyday life. Imagine an ant crawling along a telephone wire. From far away, the wire looks one-dimensional, a simple line. But up close, the ant discovers the wire has thickness, a second dimension wrapped into a tiny cylinder. Could our reality be hiding similar secrets? The math behind extra dimensions isn't just speculative, it's necessary. String theory, which aims to unite quantum mechanics and general relativity, only works if the universe has these additional dimensions. Without them, the equations collapse like a house of cards. But where are they? One possibility is they're compactified, folded into minuscule shapes at the Planck scale, 1 billion times smaller than an atom. These hidden geometries might determine everything from particle properties to the strength of gravity, which seems oddly weak compared to other forces. Some theories suggest gravity leaks into other dimensions, diluting its effect in our observable world. Then there's the brain world scenario. Picture our universe as a 3-dimensional membrane or brain floating in a higher dimensional space. Other brains might exist parallel to ours, mere millimeters away, yet completely invisible because light and matter are stuck to our brain like flies on flypaper. This idea, inspired by M-theory, an extension of string theory, could explain cosmic mysteries like dark energy or even the Big Bang itself, the result of a collision between brains. But how do we test something so abstract? Scientists are hunting for clues in particle colliders like the Large Hadron Collider. If extra dimensions exist, smashing protons at near light speeds might create particles that briefly, disappear into them, leaving telltale energy gaps in detectors. Others look for deviations in gravity at microscopic distances where the inverse square law might break down if gravity spills into extra dimensions. So far, no luck, but the search is far from over. The wildest implication: if higher dimensions are real, they could rewrite not just physics, but our place in the cosmos. Are we shadows of a richer reality? Could advanced civilizations manipulate these dimensions for travel or energy? For now, these questions hover at the edge of science and imagination, but the answers might be hiding in the quantum hum of the universe itself. Einstein's general relativity paints gravity as the bending of spacetime, a smooth, cosmic dance where planets and stars warp the fabric of reality. Quantum mechanics, on the other hand, reveals a subatomic world where particles flicker in and out of existence, governed by probabilities and uncertainty. These two theories work flawlessly in their own domains, but when they collide, the result is chaos. The math breaks down, predictions explode into infinities. And at the heart of this crisis lies a single, monumental question: what is quantum gravity? One leading contender is loop quantum gravity, a framework that reimagines spacetime itself as a network of tiny, woven loops, like an unimaginably fine cosmic mesh. Instead of smooth curves, gravity here emerges from discrete, quantized packets of space. Picture the universe as a tapestry where each thread represents a fundamental unit of space-time, vibrating and intersecting to create the geometry we experience. This approach avoids the infinities plaguing other theories by treating gravity as a quantum field with built-in limits. It even suggests spacetime has a granular structure at the Planck scale, around 10 to the minus 35 meters. But there's a catch. Loop quantum gravity struggles to explain how this pixelated reality smooths out into the universe we see. Enter string theory, the most famous and controversial candidate. It proposes that all particles, including gravity-carrying gravitons, are vibrating strings in a 10 or 11-dimensional universe. The elegance is undeniable. These strings' harmonics dictate particle properties, unifying all forces under one mathematical roof. Yet string theory demands extra dimensions curled into microscopic shapes, and after decades, we've found no experimental proof they exist. Worse, the theory allows for a staggering 10 to the 500 possible universes, leaving some physicists to wonder if it's more philosophy than testable science. Then there's the holographic principle, a radical idea born from studying black holes. It suggests our three-dimensional reality might be a projection of information encoded on a two-dimensional surface at the universe's edge, like a cosmic version of a hologram on a credit card. If true, gravity wouldn't be fundamental at all, but an emergent property of this deeper information layer. The math works, black hole entropy calculations support it, and some lab experiments with ultra-cold atoms mimic holographic behavior. But accepting this means rewriting our intuition about reality itself. Each approach has its champions and deal-breakers. Loop quantum gravity is background independent. It doesn't rely on a pre-existing spacetime but lacks unification with other forces. String theory is mathematically beautiful but untested. The holographic principle is mind-bending but lacks a full framework. Meanwhile, experiments like gravitational wave detectors and quantum foam probes hunt for clues in the void between theories. The stakes couldn't be higher. Cracking quantum gravity wouldn't just reconcile physics, it could unlock secrets from the Big Bang's first moments to the fate of black holes. Until then, the universe keeps its deepest rulebook hidden, daring us to think bigger, stranger, and bolder. The sun's corona is a cosmic paradox, a blazing halo of plasma that burns millions of degrees hotter than the star's surface beneath it. Picture holding your hand near a candle flame. You'd expect the flame to be hottest at its core, not farther away. Yet the sun defies this logic. Its visible surface, the photosphere, simmers at a toasty 5,700 degrees Celsius, while the wispy corona above it roars at temperatures over 1,000,000 degrees. This baffling mismatch, known as the coronal heating problem, has stumped solar physicists for decades. How can the sun's atmosphere be so much hotter than its surface? The answer might lie in the chaotic dance of magnetic fields and energy waves crackling through this stellar inferno. One leading theory points to magnetic reconnection, a process where the sun's tangled magnetic field lines snap and realign like cosmic rubber bands, unleashing colossal bursts of energy. Think of it as a game of tug-of-war where the rope suddenly breaks, whipping outward with explosive force. These reconnection events generate solar flares and coronal mass ejections, but they might also pump enough heat into the corona to sustain its scorching temperatures. Satellite observations have captured telltale signatures of this phenomenon, like sudden brightenings in X-ray emissions where magnetic loops violently merge. Yet some calculations suggest reconnection alone can't account for the corona's relentless heat, especially in quieter regions where the sun isn't erupting. That's where wave heating models enter the picture. The sun's churning interior is a cacophony of vibrations, sending ripples called magnetohydrodynamic waves racing upward through its magnetic scaffolding. As these waves travel into the thinner corona, their energy grows more concentrated, like ocean waves surging higher as they approach shallow water. Some models suggest this energy transfer could heat the corona, much like how microwaves agitate molecules to warm your food. The Hinode spacecraft has spotted these waves in action, with magnetic loops swaying like giant plucked guitar strings. But here's the snag: many waves peter out before reaching the upper corona, leaving gaps in the heating story. The truth might be a messy combination of both mechanisms. Perhaps reconnection dominates in active regions bristling with sunspots, while waves steady the heat flow elsewhere. Or maybe undiscovered processes like nanoflares, countless tiny explosions too small for telescopes to spot, are quietly doing the work. NASA's Parker Solar Probe, now diving closer to the sun than any spacecraft before it, is hunting for clues in the corona's searing winds. Every data transmission peels back another layer of this solar enigma. Solving the coronal heating problem isn't just academic. A hotter corona means a more violent solar wind, which can disrupt satellites, knock out power grids, and endanger astronauts. Understanding these fiery mechanics could help us predict space weather and remind us that even the most familiar star in our sky still guards spine-tingling secrets. Consciousness might be the most profound mystery in the universe, not just whether it exists elsewhere, but what it fundamentally is. We assume it's a product of complex brains, an emergent property of neurons firing in just the right way. But what if consciousness is something far more universal, woven into the fabric of reality itself? That's the bold claim of panpsychism, a theory suggesting that even the tiniest particles possess some rudimentary form of awareness. Not self-reflection or thoughts, but a basic, intrinsic experience. In this view, the universe isn't just full of conscious beings, it's made of them, with human minds merely amplifying a quality that's always been there. This idea isn't new. Ancient philosophies flirted with it, but modern panpsychism gains traction from the hard problem of consciousness. Why does processing sensory input feel like anything at all? Why aren't we just biological robots crunching data without inner experience? Neuroscience maps brain activity to thoughts, but no one can explain how electrical impulses become the taste of coffee or the color red. Panpsychism sidesteps this by proposing consciousness isn't generated, it's fundamental, like space or time. Even electrons might have a whisper of it, with complex organisms combining countless micro-experiences into rich awareness. Wild as it sounds, this could reshape the Fermi paradox. If consciousness is universal, why haven't we heard from alien civilizations? The zoo hypothesis offers a chilling answer. Advanced beings might be observing us quietly, like scientists guarding a nature preserve. They could see Earth as a cosmic wildlife sanctuary, withholding contact to avoid disrupting our development. or perhaps consciousness evolves to a point where civilizations transcend physical communication, ascending to realms we can't perceive. Either way, the silence isn't emptiness, it's a deliberate veil. Then there's quantum mechanics' strangest quandary: does consciousness affect reality? In the famous double-slit experiment, particles behave differently when observed, as if aware they're being watched. Some interpretations, like the von Neumann-Wigner hypothesis, suggest conscious observation collapses quantum probabilities into definite outcomes. Critics argue this conflates measurement with awareness, but the link remains tantalizing. If consciousness does play a role, the universe might not just contain minds, it might respond to them. Whether panpsychism, cosmic zookeepers, or quantum sentience, one thing's clear: consciousness challenges our deepest assumptions. It might not just be a fluke of biology, but a feature of the cosmos waiting to be understood if we dare to look. Long before galaxies sparkled across the cosmos, before planets even existed, the universe was a silent sea of darkness broken only by the birth of the very first stars. These pioneers, known as Population 3 stars, were nothing like the stars we see today. They were colossal, furious beasts forged from the raw simplicity of hydrogen and helium in the wake of the Big Bang. And yet, despite their monumental importance in lighting up the cosmos, we've never seen one directly. So how did these ancient giants form, and why do they remain so frustratingly out of reach? Picture the universe just a few 100 million years old, a featureless void, still warm from the heat of creation. There were no heavy elements yet, no dust, no planets, just vast, drifting clouds of pristine gas. But dark matter was already at work, sculpting the cosmic landscape. Its invisible gravitational fingers pulled these gas clouds together, compressing them until gravity alone could ignite nuclear fusion. The result: stars up to 1,000 times more massive than our Sun, burning at temperatures so extreme they would make today's supergiants look like candle flames. These were the factories that would later forge the first heavy elements, seeding the universe with the building blocks of everything to come. But here's the catch: Population 3 stars didn't live long. Their enormous size meant they burned through their fuel in mere millions of years, ending their lives in titanic supernova that scattered heavier elements into the void. This means they flickered out eons ago, leaving behind no direct traces for our telescopes to catch. So how do we even know they existed? The evidence lies in their ghostly fingerprints. When we peer at the most distant quasars, ancient beacons of light from the early universe, their spectra show a surprising lack of heavy elements. This suggests they formed in a time before supernova had enriched the cosmos, pointing back to an era dominated by these pure, primordial stars. Dark matter plays a starring role in this cosmic drama. Without its gravitational scaffolding, gas alone might never have clumped densely enough to ignite fusion. Simulations show that dark matter halos acted like cosmic nurseries, funneling gas into dense pockets where stars could be born. Some theories even suggest that the unique conditions of the early universe, its higher temperatures and simpler chemistry, allowed for stars far more massive than anything we see today. Yet for all our models, we're still missing the smoking gun, a direct observation of a Population 3 star. The James Webb Space Telescope might change that. Designed to peer deeper into the infrared spectrum than any instrument before it, Webb could potentially catch the faint glow of these first stars as they appear in their infancy, stretching back to a time when the universe was less than 200 million years old. If we're lucky, we might spot the telltale signs of their explosive deaths instead, supernovae so powerful they briefly outshine entire galaxies. Either way, the hunt for these cosmic pioneers isn't just about filling a gap in our star charts. It's about understanding the moment the universe woke up, when darkness gave way to light for the very first time. One night in August 1977, a radio telescope in Ohio picked up something extraordinary, a signal so powerful and unusual that the astronomer who discovered it scribbled, "Wow." In the margin of the printout, that single word would immortalize one of the most tantalizing mysteries in the search for extraterrestrial intelligence. The WOW signal lasted 72 seconds, blasting through the hydrogen line frequency, a band many scientists believe alien civilizations might use for communication. It came from the direction of the constellation Sagittarius, matched no known natural phenomenon, and then vanished. Despite decades of searching, it's never been heard again. Was it a cosmic hello, a technical glitch, or something stranger still? The signal's intensity followed a clear pattern, rising and falling exactly as you'd expect if it came from a fixed point in space, swept past Earth by the rotation of the planet. This wasn't static or interference, it was deliberate, narrowband, and seemingly artificial. Researchers ruled out satellites, aircraft, and ground-based transmitters. Even Soviet military activity, a popular Cold War-era scapegoat, didn't fit the data. The signal's frequency, 1,420 MHz, was significant too. Hydrogen, the universe's most abundant element, emits at this wavelength. It's like someone chose the cosmic equivalent of shouting in the quietest part of the library. In 2016, astronomer Antonio Paris proposed a provocative explanation. A pair of passing comets, 266P and 335P, could have been the culprits. Their hydrogen-rich atmospheres, he argued, might have reflected sunlight in just the right way to mimic an artificial signal. The timing was plausible. The comets weren't known in 1977 and were near Sagittarius decades later. But critics pounced. Comets don't emit narrowband signals. They produce broad, messy radio noise. The WOW signal was surgically precise. Worse, follow-up observations of similar comets failed to replicate the phenomenon. The comet theory, while creative, left more questions than answers. Then there's the unsettling possibility the signal was artificial, but not alien. Could it have been a secret military transmission or a rogue satellite? Declassified records show no known tests match the signal's profile. Its power was immense, equivalent to a transmitter billions of times stronger than anything humans had in space at the time. And why would it beam from deep space, then never repeat? The more you dissect the explanations, the more the WOW signal feels like a cosmic riddle designed to defy logic. The search isn't over. Modern projects like Breakthrough scan the skies with far more sensitive equipment, hunting for echoes of that infamous blip. Some astronomers argue we might have missed a repeat because early telescopes could only monitor one frequency at a time. Today's arrays can listen to millions simultaneously, raising hopes or dashing them for good. But until the signal returns, it lingers as the ultimate tease, a fleeting, brilliant flash that dared us to wonder if we're truly alone in the dark. Venus should be Earth's twin, a rocky world of similar size and distance from the Sun, but step onto its surface and you'd be crushed, melted, and suffocated within seconds. While Earth blossomed into a life-giving oasis, Venus became a scorching wasteland with temperatures hot enough to melt lead, sulfuric acid clouds, and atmospheric pressure 90 times heavier than ours. How did two planets born from the same cosmic neighborhood end up so horrifically different? The answer might lie in a catastrophe called the runaway greenhouse effect. And clues hidden in the geologic scars both worlds bear, or in Venus's case, the ones mysteriously missing. Earth and Venus started with nearly identical ingredients, similar amounts of carbon, water, and sunlight. But somewhere along the way, Venus crossed a threshold, a point of no return where heat trapped by its thick carbon dioxide atmosphere began evaporating any oceans it might have had. Water vapor, a potent greenhouse gas itself, amplified the warming in a vicious cycle. More heat released more vapor, which trapped more heat until the planet's oceans boiled into space, leaving behind a bone-dry hellscape. Without water to dissolve carbon dioxide and lock it into rocks like Earth's carbon cycle does, the gas built up unchecked, turning Venus's sky into a suffocating blanket. Today, its atmosphere is 96% carbon dioxide, turning solar energy into an inescapable furnace. Yet here's the puzzle. Venus should have evidence of this watery past ancient river valleys or ocean basins like Earth's. But radar maps from missions like Magellan reveal a surface oddly devoid of large-scale erosion. Instead, Venus shows vast lava plains and bizarre pancake domes, suggesting its crust underwent a dramatic resurfacing event around 500 million years ago. Some scientists think a planet-wide volcanic eruption flooded Venus with fresh lava, erasing older geologic records. Others argue that without Earth's plate tectonics to recycle crust, Venus might periodically blow its top in catastrophic outbursts, resetting its surface like a cosmic etch-a-sketch. The missing water isn't the only mystery. Venus spins backward compared to most planets, with a day longer than its year, possibly due to a colossal impact that flipped its rotation. Its clouds even host traces of phosphine gas, a molecule that on Earth is produced by microbes. Could acidic cloud layers hide floating life? Most researchers doubt it, given the atmosphere's brutal conditions, but the discovery underscores how little we truly understand about this toxic twin. Probes like NASA's upcoming Da Vinci and Veritas aim to peel back Venus's secrets, analyzing its atmosphere and mapping its geology in unprecedented detail. Their findings could rewrite the story of how planets live and die, and serve as a sobering warning for Earth's own climate future. Because Venus isn't just a cautionary tale, it's a looking glass showing what happens when a world loses its balance. And a reminder that the line between paradise and inferno is thinner than we think. The moon's surface is a graveyard of ancient scars, craters, lava plains, and towering mountains frozen in time. But scattered across this desolate landscape are bizarre, luminous swirls that look like cosmic brushstrokes. These ethereal patterns, some stretching hundreds of kilometers, glow brighter than the surrounding terrain, defying the dusty monotony of the lunar surface. No one knows exactly how they formed, but their ghostly beauty hides a violent past, one that might involve magnetic fields, comet impacts, or forces we haven't even imagined. At first glance, lunar swirls resemble cream swirling in coffee, delicate, sinuous streaks of light and dark. The most famous, Rhenar Gamma, sprawls across the ocean of storms like a celestial fingerprint. What makes them even stranger is their magnetic personality. Unlike most of the Moon, which has a negligible magnetic field, these swirls coincide with localized magnetic anomalies. This has led scientists to suspect that the swirl's brightness is a shield, a magnetic force field deflecting the solar wind's relentless barrage. Over time, solar particles darken lunar soil through a process called space weathering. But in these magnetized zones, charged particles might be redirected, leaving the surface underneath strangely pristine. But magnetism isn't the only suspect. Some researchers point to comet impacts as the artist behind these cosmic murals. When a comet grazes the Moon, its vaporized nucleus, a mix of ice and dust, could create a temporary atmosphere. Electrified by sunlight, this gas might interact with the lunar soil, altering its reflectivity in swirling patterns. The comet's icy debris could also seed magnetic minerals into the surface, explaining why swirls and magnetism go hand in hand. It's an elegant theory, except for one wrinkle. Not all swirls sit near obvious impact sites. The plot thickens when you consider the Moon's volcanic history. Some swirls snake across ancient lava flows, suggesting they're linked to long-dead magma chambers. Could underground lava have baked the soil, changing its texture? Or did volcanic gases react with the surface to create these luminous trails? The answer might lie in miniature. Lab experiments show that exposing lunar soil analogs to extreme heat can lighten their color, mimicking the swirl's glow. The truth is, we're still piecing together the clues. Missions like NASA's Lunar Reconnaissance Orbiter have mapped these anomalies in stunning detail, while future landers could analyze their chemistry up close. Until then, lunar swirls remain one of the moon's most hypnotic riddles, a reminder that even our closest celestial neighbor still has secrets written in light and shadow. Can reality bootstrap itself into existence without a creator or first cause? The idea of a self-creating universe sounds like circular logic, but some of the most cutting-edge theories in cosmology suggest it's not just possible, it might be inevitable. Imagine the ultimate free lunch, a cosmos bubbling into being from sheer nothingness, governed by laws that allow existence to emerge spontaneously. This isn't philosophy, it's physics, and it hinges on two radical ideas: quantum fluctuations and the strange role observers play in defining reality itself. Start with the quantum vacuum. Far from being empty, the vacuum of space is a seething foam of virtual particles that blink in and out of existence, borrowing energy from nowhere before vanishing again. These fluctuations aren't just mathematical quirks, they've been measured. The Casimir effect proves that even in a void, invisible forces push and pull at the fabric of space. Now stretch this idea to its cosmic limit. What if, in the infinite quantum chaos of an eternal void, one fluctuation didn't cancel itself out? A tiny bubble of space-time could inflate exponentially, fed by the negative pressure of its own gravitational field. Voila, a universe from nothing, no divine spark required. But here's where it gets trippy. Quantum mechanics insists particles exist in superpositions, all possible states at once until observed. This led physicist John Wheeler to propose the participatory universe hypothesis, that conscious observers might be necessary to collapse quantum possibilities into concrete reality. In this view, the universe couldn't fully exist until life evolved to perceive it. It's as if the cosmos needed us to wake up and say, yes, this is real. Critics argue this smacks of anthropic narcissism, but the math hints at eerie connections. The constants of nature gravity, the speed of light, are fine-tuned so precisely that any tiny change would make life impossible. Coincidence or evidence of a universe that requires observers to complete its own existence? Then there's loop quantum cosmology, which rewrites the Big Bang as a big bounce. Instead of a singular beginning, this theory posits an endless cycle where collapsing universes rebound into new ones. Time becomes a Möbius strip, with each iteration tweaking the laws of physics slightly. No creator needed, just endless cosmic respiration. The implications are dizzying. If universes can self-generate, we might inhabit one of countless others in an infinite multiverse. Some would have different physical laws, rendering them barren. Others, like ours, hit the jackpot for life. It's the ultimate cosmic selection bias. We exist because our universe's rules allow it. Yet the question lingers, can nothingness truly create something? Even quantum vacuum fluctuations rely on pre-existing laws, a framework enabling their dance. Where do those come from? The universe might not need a creator, but it may need meta-rules we've yet to uncover. Until then, the mystery of existence remains science's most profound frontier. Black holes are cosmic shredders, tearing apart anything that crosses their event horizon, or so we thought. The fate of information in black holes might be the most mind-bending puzzle in physics, forcing us to question whether the universe forgets. It all started with Stephen Hawking's shocking realization in the 1970s. Black holes aren't completely black. They emit radiation, slowly evaporating over eons. But here's the catch. If a black hole vanishes, what happens to all the information it swallowed? Quantum mechanics says information can't be destroyed. It must be preserved, scrambled, or somehow returned. Yet Hawking's calculations suggested it simply disappears. This clash between quantum theory and general relativity became known as the black hole information paradox, and solving it might rewrite the laws of reality. Hawking radiation itself is bizarre enough. Imagine empty space near the event horizon, where quantum fluctuations constantly create particle-antiparticle pairs. Normally, they annihilate instantly, But if one particle falls into the black hole while the other escapes, the black hole loses mass, radiating energy as if it were a warm stove. The problem: the escaping particles seem random, carrying no trace of the star, planet, or spaceship that originally fell in. It's like burning a library and claiming the smoke contains every word of every book. That can't be right. Quantum physics insists information is immutable, never erased, only transformed. Enter the holographic principle and add S/CFT duality, a radical idea from string theory. It proposes that all the information swallowed by a black hole isn't lost inside but encoded on its event horizon, a two-dimensional surface storing a 3D universe's data like a hologram. The math is stunning. A black hole's interior could be a projection of information dancing on its boundary. If true, even as the black hole evaporates, the information isn't destroyed, just remixed into Hawking radiation in ways we don't yet understand. But then there's the firewall paradox. If information is preserved at the horizon, what happens to an astronaut falling in? Quantum mechanics demands a smooth, uneventful passage. Einstein's no drama rule. But preserving information might require an inferno of high-energy particles at the horizon, incinerating anything on contact. Both can't be true. Is space-time smooth, or is it a lethal data-preserving barrier? The stakes couldn't be higher. If information can vanish, the foundation of quantum theory cracks. If it's preserved, we might uncover a deeper layer of reality where space-time itself is emergent, a shadow play of quantum bits. Every new twist, from wormholes encoding information to quantum teleportation tricks, hints that black holes aren't cosmic dead ends. They're the universe's most provocative teachers, challenging us to rethink everything we know about information, gravity, and the fabric of existence. The universe seems suspiciously hospitable to life, almost as if someone dialed the cosmic knobs with precision. Take gravity, for example. If it were even slightly stronger, stars would burn out too quickly for life to evolve. A fraction weaker, and galaxies might never have formed. The same goes for the strong nuclear force. Adjusted by a hair, and atoms couldn't stick together. Even the cosmological constant, which governs dark energy's push, is fine-tuned to 1 part in 10 to the 120. That's like firing a bullet and hitting a target a trillion light-years away. These razor-thin margins aren't coincidences. They're conditions without which we wouldn't exist to ponder them. But why? Is this evidence of a grand design or just cosmic luck? Enter the anthropic principle, the idea that our very existence filters what we observe. In its weakest form, it's almost tautological. We measure these constants because, well, we're here to measure them. If the universe were hostile, no observers would arise to question its harshness. But the strong anthropic principle goes further, suggesting the universe must allow life, implying a deeper, almost purposeful framework. Critics argue this skirts close to creationism, invoking a designer without evidence. Yet supporters counter that physics itself hints at something extraordinary. The fine structure constant, which dictates how atoms interact with light, is exquisitely balanced. Tweak it by 4% and carbon. The backbone of life couldn't form in stars. This conundrum fuels the multiverse hypothesis. If countless universes bubble into existence, each with random physical laws, statistically, a few will hit the life-friendly jackpot. We just happen to live in one. It's the ultimate cosmic lottery, trillions of dead universes for every one like ours. String theory's landscape of possible universes, some with 10 dimensions, others where gravity repels, lends mathematical weight to the idea. But here's the rub. If the multiverse can't be tested, is it science or philosophy? Some propose hunting for bruises in the cosmic microwave background, collisions with other bubble universes, or anomalies in particle behavior that betray hidden dimensions. So far, no smoking gun. Then there's the theological angle. Fine-tuning resonates with the idea of a creator, an intelligence setting the dials. But science balks at invoking the supernatural. It's a conversation stopper, halting inquiry. Instead, physicists like Leonard Susskind suggest a middle path. Perhaps the laws of physics aren't arbitrary but emerge from deeper principles we've yet to uncover. Just as thermodynamics arises from atomic chaos, maybe life-friendly constants are inevitable in a theory of everything. The debate rages because the stakes are cosmic. If fine-tuning is real, it reshapes our place in the universe, from accidental flukes to potential inevitabilities. Every new discovery, from exoplanets to quantum gravity, nudges us closer to an answer. Until then, the universe's perfect imperfections remain its most tantalizing clue. From the invisible grip of dark matter to the eerie silence of alien civilizations, these 30 unanswered questions reveal just how much we've yet to uncover about the cosmos. Each mystery is a humbling reminder that for all our knowledge, the universe remains a vast and enigmatic frontier. We've stood at the edge of black holes, peered back to the dawn of time, and mapped the unseen forces shaping reality, yet every answer seems to unlock 10 new puzzles. Think about it, we don't even know what makes up 95% of the universe. Dark energy accelerates cosmic expansion, but we can't detect it directly. Black holes defy the laws of physics, swallowing information without a trace. Fast radio bursts pulse across the void, flashing signals we can't decipher. And then there's life itself. Did it arise from Earth's primordial soup or hitchhike here on comets from distant stars? The more we learn, the clearer it becomes. We're only scratching the surface. But that's the thrill of exploration. Every unanswered question is an invitation to imagine, to theorize, to push the boundaries of what we think is possible. Maybe you're fascinated by the multiverse, where infinite versions of reality might exist. Or perhaps the wow signal's tantalizing blip keeps you up at night, wondering if we've already heard from another civilization. Whatever sparks your curiosity, remember, the greatest discoveries often begin with the courage to say, "I don't know." So let's keep asking, keep searching, and stay awestruck by the cosmos's mysteries. Drop a comment below. Which of these questions fascinates you the most? What cosmic puzzle do you hope we'll solve in your lifetime? The universe isn't just a collection of stars and planets. It's a story we're all writing together, one question at a time. And who knows, the next big breakthrough might start with you.